Today I've got two big problems for you. You can grab a pen and paper to follow along or just watch. At the end of each problem, I'll show you the full problem with its solution. And don't forget, you can always hit pause if I go too fast. Okay, our first problem is a funky looking cable system suspended from a wall by 2 points, one at A and at D. It's being held up by a 25 kilonewton force that's applied at point B at an angle of 30 degrees from the horizontal. Then there's a horizontal force P that's being applied at point C, but we don't know what that force is. We want to know what force P is required in order to maintain this cable geometry. We start with global equilibrium. In the x direction, we have the x component of our 25 kilonewton force going in the negative x direction. In that same direction, we have the force P, and in the opposite direction, we have our reactions at the support points A and D. In the y direction, the y component of our applied force is 25 times the sine of our angle with the horizontal. And again, we have our reactions at A and D. We'll keep track of all our equations by numbering them as we go. Now we're ready for our last global equilibrium equation. We can take the moment about any point and it will be equal to 0. We'll pick point D. Taking the moment about point D will give us a 0. We're going to assume that any force that causes our system to rotate about point D in this direction is positive. So to start, we've got our force AX, and it acts at a distance of 4 plus 6 plus 1.5 meters from D, and it causes a rotation of the system this way, which is negative. Our next force is going to be the vertical component of our 25 kilonewtons. It will again cause a negative rotation about point D. And it acts at a distance of 2.5 meters from D. Then we've got our horizontal component of our 25 kilonewton force. If I were to pull this way, it would cause a positive rotation about D. And it acts at a distance of 4 plus 6, which is 10 meters. Lastly, we've got our horizontal force P at joint C, and it again is positive and acts at a distance of 4 meters from point D. And all of that will equal 0. So I'll just get out the way. You can see that the only variables we have in this equation are AX and P. So we can simplify this to look a lot nicer. And we're ready for our next step. All we've been asked to find in this problem is the force P. So we're going to try not to get distracted by all the other things we could solve for in our mission to find P. To do that, we'll have a two-point strategy. First, we're going to use our reaction points. Because we know the geometry at those points, we can simplify our reaction forces in terms of things we know. Second is that any equilibrium equation we write, we're going to try and write it in terms of the unknown force P, instead of in terms of unknowns like TBC, TAB, or TCD. That will let us solve directly for P. Starting at joint D, we know that for equilibrium, TCD has to be equal and opposite to the combined effects of dx and dy. That means that the tangent of the angle with the horizontal, which we know from geometry, will be equal to the tangent of that angle using the reaction forces at D. So we can equate them and rearrange them to give us a nice expression for dy in terms of dx. Next, we can move on to joint A, where we do the same thing. The tangents of the angles on each side are equal, so we can equate them to get that AY is equal to 0.6 AX. Let's take a step back and think about what we know and what we're trying to know. We're trying to find the force P by making equilibrium equations with as few unknowns as possible. In fact, we're trying to use only the unknown P if possible. We've already found AX in terms of P. Is there any way we could find the force dx in terms of P? Like, what if we only looked at part of our cable system? We can cut our system right here so that we're only looking at the bottom part. The part that has a P, a dy, which we already have in terms of dx, and a dx. So let's cut our system and take a moment. If we cut the segment BC, we can look at just the lower portion of the cable system. Now we can take the moment about point B. Since the tension in segment BC goes right through point B, we don't need to include it in the equation. That gives us an equation in terms of P, dx and dy. Now we can use substitution to write the equation in terms of just dx and P, which lets us write dx in terms of P. This is super neat, and I'll show you why. We now have enough equations with our variables in terms of P that we can write an entire equation in terms of just P. That will let us solve for P. We substitute our equations, collect like terms, and solve to get that P is equal to 56.6 kilonewtons. Nice job! Now, here's the whole problem together. You can pause and review. Notice that we didn't really even need to look at joint A in order to get our answer. For our second example, we have a cable system suspended at points A and E. Segment CD is completely horizontal. We want to find out what unknown vertical forces at point B and point D are required in order to maintain this geometry. We also want to know what the maximum tension in our cable system is. So, big problem requires big strategy. One way to solve this problem would be to do equilibrium at each of our joints and make a system of linear equations. Then you could use linear algebra to solve your whole system all at once. Or you could instead go joint by joint again, but try to use as few unknowns as possible. So looking at our system, what can you tell me? In the x direction globally, we have no applied forces, right? So if we were to draw a free body diagram, we would know that the forces AX and EX must have the same magnitude and be in equal and opposite directions. That means that anywhere along our cable system, if we were to make a cut, the horizontal component of our tension would have to have that same magnitude. So at each joint equilibrium, we can write our equations in terms of one of these values. I chose to use EX. So we can write all our equations using EX, and then all we have to do is solve for EX in order to get everything we want to know. Sounds pretty good, right? Okay, let's get started, and remember that you can pause at any time you need more time. It's always good to start with global equilibrium. We've done X, and here's why. We're sticking to our plan of writing things in terms of PB, PD, and EX as much as possible. Here's our global moment equilibrium about point A. Once we plug in the numbers for each of the x distances, it simplifies into something not too bad. Remember, our goal is to get everything in terms of PB, PD, and EX. Two of our equations so far have also had an EY in them. We're going to try and get rid of that first. We make our first cut right through the segment CD. With this cut, we can get EY in terms of PD. Using the sum of forces in the y direction, we get that EY is equal to PD. We can take this and plug it into equation 2 to get rid of that EY from before. And just like that, bam! We can simplify it with those PDs canceling each other. We update our list of equations, then we're ready to start going through our joints, starting at E. Remember, the goal is to get all our forces in terms of EX. To keep this joint still, the x component of the tension in segment DE must be equal and opposite to EX. Since all the dimensions in our cable system are known, we can figure out the angle theta if we want to. So we can treat it as a known. That means that TDE can be written in terms of EX. Ta-da! Next, we'll look at joint D. Remember, we said that all horizontal tension components are equal to EX. Since segment CD is horizontal, tension CD has to be equal to EX. Now, can we get PD in terms of EX? For D to stay still in the y direction, the y component of TDE must be equal to PD. We get the y component by projecting the tension vertical, using the sign of angle theta DE. We can substitute from 5 into 6 to get rid of TDE, which gives us PD in terms of EX. Okay, we could go on to the next joint, but I want to make this look a little simpler first. Remember that sine theta over cos theta is equal to tan theta? Well, we can use this to get rid of the angles in our expression and stick in some cold, hard numbers. Sine theta over cos theta gets replaced with tan theta. Then tan theta gets replaced with actual numbers. Much better, right? Okay, we've got PD nicely in terms of EX, so we're ready to move on to joint C. From joint C, we're going to be repeating the same steps we've already done. We use equilibrium in the x direction to get the tension in BC in terms of EX. We could solve for theta if we wanted, but we'll leave it for now since since we're going to combine it with sine again at joint B. I like to avoid solving for angles until the very end. I find them messy to work with and often they'll cancel out anyway. Now we can use this joint to solve for our infamous EX. Using equilibrium in the y direction, we know that the y component of TBC has to be equal and opposite to the force applied at C. We can substitute that into the equation for TBC that we just found, and turn that sine over cos into a tangent, which we can once again use real numbers for. Now we can solve for EX, turning this equation into a beautiful value for EX. Now we're ready to move on to our next joint. We're going to jump to joint A. That's because at B we have two unknown tensions to deal with, TAB and TBC. We want to get both of those in terms of EX before we head to joint B. We're going to use equilibrium in the X direction at joint A to get us what we want. We can sub in that AX has the same value as EX and solve for TAB. At this point, we now have all our cable tensions in terms of EX, which we already know. Finally, we've reached joint B. Here, we're going to do more of the same. Let's get PB in terms of EX. We can use equilibrium in the y direction. We project our tensions to get the y components by using the sine of their angle with the horizontal. Then we're ready to substitute those tensions in terms of that notorious EX. We convert those fractions into some tangents. Then we throw some numbers in to those tangents. And we combine our like terms to solve for PB. Here comes the fun part. See all these equations that we found by going joint to joint? Well, now we've got all the power. We can solve them all with EX. Okay, so what do we actually care about? We're asked for the forces PB and PD to find the maximum tension in the cable. Using our equations for PB and PD, all we have to do is plug in our value for EX. We get that PD is 35 kips and PB is 13.125 kips. Our last step is to find the maximum tension. Let's bring back our tangents that we used along the way to see which segment will have the highest tension. Remember, in our entire system, the horizontal component of tension is constant. To maintain that constant horizontal force, when a section of cable is sloped upward, the overall tension in the cable has to increase. That's because the more sloped it is, the higher the proportion of that section's tension goes toward the vertical component. So the steeper the cable segment is, the larger the overall tension in that segment becomes. So looking at our tangents, which angle is the steepest? Theta DE. It's the biggest tangent and the biggest angle. Knowing that, all we have to do is use our equation for TDE to solve for our maximum tension. Calculating our angle and filling in EX, we get that our maximum tension is 41.6 kips. Congratulations! That was a heck of a long problem, but we got to the end. I know it's lots of hard work, but remember, the more you practice, the less stressed you'll be for your next exam.